Okay, and I'm just waiting for that red button to go to show that it's recording. Yep. Right. Okay, so welcome to this organic overview. So I'll do it very similar to what I did for the 3.4 exam, where I'll be flicking through a whole lot of past exam paper questions. For the 3.4, we divided it into 10 topics. For the 3.5, it's divided into 6 topics, but some of them are sort of bigger topics. The first thing, though, you can see on the screen is something you should be able to download from the CHO 3052 module, and it should be near the end, either the revision or the very last lesson, somewhere around there. So what you need to know is the reaction schemes, because you're guaranteed to be asked questions about 1/3 of the questions will be about reactions of some sort. So make sure you know these. So what I've also done here, you've also got to know the type of reaction. So not just simply I need sodium borohydride to go from a ketone to a secondary alcohol, but that is a reduction reaction. So there is quite a bit of learning work. And what you can do is, if you've already printed this, sorry, because it's back to back, what I've got here are little cards. So for instance, this is a primary haloalkane. This is an alkene. I've made it slightly different from a what I've tried to show here, an asymmetric alkene, and this one could be a symmetrical one. Or if you like a terminal alkene or not. This is important for the Markovnikov and the Zaitsev rules, where you've got, if something is asymmetric, then what is the major product or what is the minor product. So if you flip to the other side, what I've got, now remember this was the primary haloalkane. It was on this side on the previous one, because when you do back to back, it sort of swaps over. So when you do the primary, if you learn about primary haloalkanes, think of all the ways you can react it. And I've done it as sort of color coding. So red, you'll notice, is an elimination. Green is substitution. And blue is addition reactions. So I've done where you can start off with a primary haloalkane and the products you can form using these reagents. And I've also done how to make a primary haloalkane. So you can make a primary haloalkane from an alkene, a terminal alkene. Okay, so it's got to be one where the double bonds, CC double bonds at the end. Or you could make a primary haloalkane from a primary alcohol. So if I go back to this over here, where we had haloalkanes, there were different ways. These are the reactions. You can make an amine with it, or you can make an alkene, or you can make an alcohol with it. So those were those reactions. Or to make, there were those two ways you could make a primary haloalkane, by going from a primary alcohol to the primary haloalkane, or from an alkene, although it's in particular a terminal alkene, to the haloalkane. So use those cards. Now, I also suggest you learn not just by functional group, but that you also learn by the reagent. So when you've got the reagent, sorry, good luck, Leif. Sorry, my son's just going for his exam. Right, so you can also do by reagents. If I go further down, okay, these are still all the functional groups. The major and minor products are ways you can do that. I've just got to carry on going down. Here are the reagents. So you can learn by reagents, and if you flip to the other side, this shows all the times you use concentrated sulfuric acid. So there are different ways you can use concentrated sulfuric acid, or different ways you can use thionyl chloride, and so on. So any questions on that, on where to find it or how to use it? Because this is very useful for learning the reactions. All good, I hope. Right, you can always ask your teacher if you're not sure where. Right, so that was the first thing that you do. Okay, acidified permanganate and acidified dichromate can oxidize primary alcohols. Correct. According to Study It guides, only acidified permanganate can oxidize secondary alcohols. No, dichromate can also oxidize. Permanganate is a bit of a stronger oxidant, so it doesn't need as harsh conditions. In fact, but if you just simply reflux, in fact, with both of them, with both acidified dichromate and acidified permanganate, you will need to reflux. And that's also another question that comes. When do we distill? When do we reflux? Why do we reflux? So because organic molecules are basically breaking covalent bonds, we need that heat, that energy to break those bonds. So both of them will oxidize, primary and secondary. You just need to reflux for perhaps longer for the acidified dichromate. Where you would also use for primary alcohol, you'd never use acidified permanganate when trying to make the aldehyde. You would always use the dichromate because it's a bit of a weaker one, and you would do this under distillation. So the moment you made the aldehyde, because it's got a lower boiling point, because it doesn't have hydrogen bonding, it is going to distill off and not react further and get oxidized. Okay, because past papers say acidified dichromate, yes, acidified dichromate can also be used. So both acidified dichromate and permanganate for both primary and secondary alcohols to oxidize further. Right, I hope I cleared that up. Yep. Okay, so let's now go to the past questions. Again, if you want to just simply achieve this paper, then you actually only need around about 8 to 9 points. I would always aim for 9. But you can see that it's quite easy to pick up points. To get excellence, you must know your reactions. Okay, that's absolutely, you need to know them backwards because you've got to normally get everything correct for that reaction scheme to get an excellence point. So let's start off with how a question, a paper normally starts. You normally open the paper, and normally the first thing it does, it gives you a table of either 3 or 4 substances where they give you usually some of them the name. So you'll see these in black are the name, and or these were the ones. So 2-methylbutanoic acid and a structure and another name and a structure. And you'll notice you've always got to get 3 correct. If they gave you 4 for an achieve point, or if they give you 3 items, then you have to get 2 out of the 3 correct. They are not too fussy if you leave out, say, a hyphen. So if you, instead of saying 2-methylbutanoic acid, they're not going to mark that wrong, although strictly speaking, it should be 2-methylbutanoic acid. It will be marked wrong if you simply said methylbutanoic acid, because you don't know, is it on the 2nd carbon or is it on the 3rd carbon? So the moment there's a choice, you have to put in the number. Similarly for hexanone, if you simply said hexanone, we don't know if you meant hexane 2-one or hexane 3-one. So you've got to put the number in, otherwise it will be marked incorrect. Okay, so this is fairly straightforward. They will nearly 99% of the time always ask you for an ester. So make sure you know how to name esters, although quite frankly, usually because you always are given one to get wrong, if you stuff up the ester, because that's always the hardest one to name, it's not a problem. Remember, it's the bit that's single bonded to the oxygen that always comes first. So it's the methyl and then the one with the carbonyl is the main thing. So this is methyl butanoate. So I'm not going to really go over the naming. The other thing I do want to say is when you draw, always try, if you don't know it backwards, is draw every single bond. Don't do what we call semi-structural like this. What I suggest you do is always draw something like, so if I was drawing this one, then you would go C, draw 4 bonds, C, draw 4 bonds, C, draw 4 bonds, okay, and then you go N must have 3 bonds, and now you fill it in with the hydrogens. Make sure you do the hydrogens. If there are no hydrogens, it's marked wrong. Okay. The reason being is if you just sort of do them in a line like this, it's very easy to say CH2, 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 and then put in a double bond, or, you know, and really stuff up the number of bonds. So if you draw out what we call the full structural formula, then you're much less likely to make a mistake, because this really is a very easy achieved point, and you don't want to stuff it up by a silly mistake because you didn't count properly. So drawing the full structural formula really helps. Okay, right. Now, the next question will be a question on isomers. Now, it could be broken up in different places, so it doesn't necessarily be in question 1. It may be at the end or in the middle question, or it could be part of it is in question 1 and part of it in another question. So by isomers, the type of isomers you can be asked for are the constitutional or structural, and that means when they've got the same molecular formula, but the atoms are connected differently. Then you've got what we call the stereoisomers, which are the enantiomers or optical isomers, same thing, and the geometric isomers. So that's got the same molecular formula. The atoms are connected in the same way, but they're connected differently in space. So for example, what I've got here, where are they? Hopefully you can see this. So what I've got, and I'll just hold it to this carbon. With this carbon, I've got a blue thing, a green thing, an orange thing, and then I've got this methyl on the end that I'm holding. This has got exactly the same thing. It's got a blue thing, it's got a green thing, an orange thing, and the methyl I'm holding. So it's the same molecular formula. They are connected in exactly the same way in terms of that carbon is attached to a blue thing, a green thing, and an orange thing, okay? But they are arranged differently in space. So when I try and superimpose them, where I'm trying to match the methyls and I'm matching the blue, notice that the thing coming towards you, the top one has got an orange thing pointing towards you, and the bottom one has got a green thing pointing towards you. So these are what we call optical isomers or enantiomers, because you can't superimpose them. Okay, so that's a question you will always be guaranteed to ask. Something on enantiomers and something on constitutional isomers. And occasionally they will do geometric, but geometric is considered more level 2. You are supposed to know level 2 for this level 3 exam, but it's, you know, that is not as likely. So how will we be asked? Let's go to an enantiomer one. So you will need to say why this is an enantiomer, okay, and draw them. So Y is, it must have what we call a chiral carbon, which is a carbon atom with 4 different groups on it. Okay, not different functional groups, just different groups. So that's COOH is different to OH, which is different to methyl, which is different to hydrogen. So it's got 4 different groups on it. And the easiest way to draw them, because quite frankly, these angles are terrible. If you looked at this, there's no ways you could ever show something like that. So the easiest is to put that chiral carbon in the middle and then draw 4 bonds at right angles. Well, perhaps just draw 2 at right angles, because the other one you must be dashed where it's biggest, closest to the carbon, and then it goes to nothing. So this is like showing it's going into the page. So this will be a methyl, and this could be, say, a COOH. And then the other two is you've got to show it coming out of the page. So you make a wedge where the thin end is closest to the carbon. So this could be, say, the OH, and that's the H. Okay, so now when you want to do the enantiomer, you simply swap 2 around, the top and bottom or the left and right. So I'm going to just swap the top and bottom so that, because it's easiest. So that's the OH, and then that's, but you have to, if you're using this method, you have to make sure you've got the wedges with these going biggest, the ones that are dashed, biggest part closest to the carbon, the ones that are solid wedges, smallest part closest to the carbon. Okay, the other thing is please make sure that every carbon has got 4 bonds and every hydrogen only 1 bond. So you can't write, for example, don't write something like this, HOOC, because that's rubbish, because I'm saying then that H has got 2 bonds, which is not correct. So this is normally a merit level question, and if you practice it, these are dead easy to draw, particularly if you use this method. Otherwise, you know, you've got to do pretty much 109 degrees angle there, and ideally it should be something, a wedge coming out and then the dotted going back. So if I show it over here, can you see this is the 109 angle over here? This orange one is going back away from you. So you can see the green one nearly overlaps the one going to the back. And then this green one is coming out towards you. So that's the other way of drawing it. Okay, then the question about this always says, usually has some sort of question about explain how you can distinguish between the two. Now, a lot of people will say, oh, you can distinguish between them because they're non-superimposable. Well, I'm sorry, you actually cannot see a molecule. You don't have those X-ray eyes or whatever to actually see the individual molecules, so you cannot superimpose them. You can only superimpose models. So the way you distinguish them is you put them into a polarimeter and shine plain polarized light. So use that term, plain polarized light. And what each enantiomer does, it simply changes the plane, it rotates the plane of that polarized light. One will rotate it to the left and the other will rotate it to the right. And I would say, you should say, by the same amount. So one will rotate it, say, to the left by 10 degrees and the other one will rotate it to the right by 10 degrees. So that is, to me, an easy merit level question, because you just have to look at these, look for the carbon that has got 4 different groups on it, and then draw the diagram, and you just can learn this bit off by heart. You know, polarimeter, plain polarized light, rotates to the left and rotates to the right by the same amount. You know, learn those key phrases. The other way they can ask you is they can give you, and now this is not on enantiomers, this is now on constitutional isomers. They can ask you to draw different constitutional isomers by giving you a molecular formula. And then to make it harder, they give you properties for the particular ones they are looking for. So key things you need to look for, is it straight chain or branch chain? So by straight chain, we just mean they all connected in a row, no jumps. Branch chain means that you can't like go along without jumping. And here you've got to go up and then down. So the moment you've got to jump, it's branch chain. So that is important. Always look to see, is it straight or branched? So you'll see here's another one that's branched, okay, and here's another one that's straight. And then you've got to look to see what the property is. So this is going to form bubbles when it's connected with a carbonate. Now, hopefully in level 1 science, you learned acid plus carbonate gives salt plus water plus carbon dioxide. So that's carbon dioxide gas. And so this must be an acid. So the only acid you know about is the carboxylic acid. So here you would just simply draw 5 carbons in a row because you're told it's 5 carbons. You know it's got to be an acid, and an acid is always on the end. Okay, you know it's going to be straight chain. That's why it's 5 carbons in a row. And now you just simply complete the hydrogens. So you check that you've got 4 bonds for every one. Make sure that your bonds are between the bonding atoms. And again, if you do a full structural, then you are going to get them bonded correctly. And there's your answer for the first one. Here, you would say a branched chain with 2 different functional groups that cannot react with either permanganate or bicarb, sodium carbonate, washing soda. So it can't be an acid. It can't be an alcohol. It can't be an aldehyde, because an aldehyde can also react with that. Okay. Okay. It can't be, let's be specific. It can't be a primary or secondary alcohol. It can be a tertiary alcohol. So because it's branch chain, we can have a tertiary alcohol. And because we need to have 2 of these, the only other option we've got is a ketone. The reason why I didn't choose an ester, because an ester is just a one functional group and uses up both those oxygens. And there's no ways I can do another functional group. So here, I'm going to go 1, 2, 3, 4. I've only done 4 instead of 5 because I need to do a branch chain. So I put in another carbon in there for a branch chain. So I've got to make a tertiary alcohol. So I'm going to put my tertiary alcohol there. And then I've got to put in my ketone. Now I make sure every carbon has got 4 bonds. That one already has got 4 bonds. And this one already has got 4 bonds. And now I add in my hydrogens. And as you add in your hydrogens, count them up to make sure that you've got 10 of them. And you should have 10. Okay, so that's the way you do these sort of things. Just go logically through it, and you should then be able to get at least some of it correct. You'll notice you do need structural formulae correct for an achieved, and correct functional groups for at least. So it's easy to get to. Every bullet point is a point. So if you've got your, say, your enantiomers correct, you've got your naming correct, you've already got, if you've got these 2, you've already got 4 out of the 8 or 9 that you need to achieve. Now I know you want to do better, but I'm showing how easy it is to actually pass. So here, look for other things. So here it says smells pleasant. So you've got to know all the properties. That hopefully you'll think of smells pleasant. It's going to be an ester. Okay. And not only that, it has to be an ester, but it must also have a chiral carbon in it. Okay. So for instance, none of these carbon atoms are chiral. So you've got to be careful that you make sure that you've got 1 carbon atom in there with 4 different groups. Okay, I don't want to use up too much time because there's so much that we can still do. So there's all that. We've done the enantiomers, and so these also show it's, can you see it's the same sort of things that come up again and again and again. So you can rote learn certain things. Okay, here we've got again, you've got now C5H10O. So not O2, it's just O. Can you draw the following? A branch chain. Now this one's a bit tricky, a 5-carbon ring cyclic molecule. So for that was a bit sneaky, I will say. So that's 1, 2, 3, 4, 5. So 5 carbons in a ring, but each carbon must still have 4 bonds. So, you know, you would start like that. Okay. Now, you will always get a question on some sort of identify or distinguish between. So you could be saying, hey, I've got this compound and that compound, how would I distinguish between them? Or they say, I've got an unknown compound and I've done all these tests on it. Tell me what it is and why you worked it out. Or it could be, I've got 3 or 4 unknown compounds. Devise a scheme that you can follow to know which each, so you can find out what each one is. So you'll always get something along those lines. And the best way is just to try and work out, you know, so here it reacts. So again, this must be an acid. Okay. When you heat it with acidified dichromate, there is a reaction. So we know it goes from orange to green, so it's being oxidized. But it does not react with Benedict's. Now that Tollens, Benedict's, and Fehling's are the tests for aldehydes. So we know it is not an aldehyde. So it probably is a ketone, or it is and well, when it gets oxidized, it forms a ketone. And if it gets oxidized to form a ketone, it means I must have had a secondary alcohol to be oxidized, because only primary and secondary get oxidized. So my primary alcohol would form an aldehyde if we were distilling it, which would react with Benedict's. If we went all the way through to a carboxylic acid, then it wouldn't react with Benedict's either. So I would go and look a bit more detailed to see what else is there. X undergoes an elimination reaction with conch sulfuric to produce 2 organic products. So, you know, I would suggest just jot ideas down. So can you see what they've done here? There's my carboxylic acid. So this is the answer. So that was that, the carboxylic acid from this point. And remember, I said because it's got to form a ketone, it will have to be a secondary alcohol. And you have to explain. So remember, to get an excellence, you have to give as much detail as possible. Go through and check whether your answer has discussed major or minor products. Have you discussed that? Have you drawn the structural formula for all the organic products? So that is for all of these. When it undergoes elimination, when it undergoes the reaction with carbonate, or when it gets oxidized with the dichromate. You've got to make sure you've written equations, or at least the products, because they just really want the products for each one. So if you want your excellence, everything needs to be there. If you've often there are 2 excellence opportunities. So if you perhaps got one slight little thing wrong, you might still get an E7. Overall, if you got the other excellence, but otherwise you've got to get both excellence opportunities in order to get an E7 or an E8. The E7 just means you can have a slight problem with it. Now, do I need to go over major and minor products? Okay, no, right. Okay, so here now is Or did I go backwards? Okay, sorry, this is all under enantiomers. This should have actually come under enantiomers. Oh, I need to reorganize this. This should have been under enantiomers. Okay, right. Now over here, there will generally be some sort of question on practical technique. And this is where the Te Kura students have the hardest thing, because you've actually never been in the lab and actually physically connected this glassware together and actually did an experiment. All you've been able to do is watch videos, and that never sits in your brain to remember as easily as if you actually done the practical. So but it's normally fairly straightforward. This is a distillation where something boils off, and as it's stop it up there, so it can't carry on going further up, but it's goes there, the gas then moves down here, and this is a cooling tube. Water flows in from the bottom and then flows out at the top, and it cools down the gas, so it forms a liquid and it drops off in here. So this is a distillation which, when there's a product that's formed that's got a lower boiling point, so like say we're going from an alcohol that has a higher boiling point to an aldehyde, which is a lower boiling point. As soon as the aldehyde is formed, it's going to boil off, condense, and drip down here. If, however, you want to take your alcohol and you don't want the aldehyde, you want it to go all the way through to the carboxylic acid, if it was a primary one, or even if you're going from a secondary to a tertiary, you want it to happen as quickly as possible. You've got to supply heat because you're breaking covalent bonds. So you just simply use a reflux. So what will happen, this goes straight up and down. So as you form the aldehyde, it's going to go up here. This again is a cooling tube. The gas condenses and drops straight down again. And then it, so it just keeps it, and then the aldehyde then will carry on reacting with the dichromate or the permanganate, and it just goes up and down until all the alcohol, all the aldehyde that's formed, it'll all now have been converted to the carboxylic acid. Okay, so you do need to be able to recognize the apparatus, distillation and reflux, and be able to explain where you would use them. Okay, so distillation is when you evaporate the product off as soon as it's formed, and you condense it in that cooling tube, and it's based on their boiling points. You can't use a distillation if the product has got a higher boiling point than the reactant, because what's going to happen is the reactant's going to boil over, and you're not going to get a reaction. So alcohols to aldehydes is fine. You can't do alcohols to carboxylic acids by distillation, because the carboxylic acid has got a higher boiling point than the alcohol. So, you can never use a distillation to go from alcohol to carboxylic acid. Okay, so this is, again, the more detail, the more obvious detail you give, the more likely you're going to get excellence. So here are different ways. This is a triglyceride. When do we use reflux? This was part of actually a polymer question, but I've dumped that in here. Here's again an aldehyde done by oxidation. So of course, whenever you make an aldehyde from a primary alcohol, you're going to need to distill. If you want to make the carboxylic acid, you reflux. So here again are some questions about it. Right. So you'll notice there's always something to explain about the practical work. Again, there could be an ester. When you're reacting an alcohol together with a carboxylic acid to form an ester, the ester has the lower boiling point, so you would use distillation. You would dump in the carboxylic acid and the alcohol here with your conch sulfuric acid, and would boil it away. And the moment the ester is formed, because you don't want the ester to react further with the acid, so the moment the ester is formed, it's got a lower boiling point, so it's going to evaporate, condense here, and drop off. Just pop in any questions if there's something you're not sure about. Okay, and here's the identification procedure again. I must have muddled this up, so I will clear this up again and when I send out my email with a recording. Here's a case where you've got two substances, propanol and propan-2-ol, or methyl ethanoate and propene. How would you distinguish between them? And as I say, always tick off these bullet points to see if you've done everything. Like, did you actually write your observation? That's a common one that gets missed. This is the color changes, the state, any changes in state, any gases being formed, any solids being formed, and so on. Okay, have you drawn the structural formulae for the organic products? Did you say, is it an oxidation, reduction, acid base, so on, substitution, elimination, or addition reaction? So notice you've got to know the Tollens, the Benedicts, or the Fellings. The Benedicts and the Fellings both are based from the copper 2 ion to the copper 1 ion. So it's always going from blue to brick red, because blue is copper 2 plus, whereas the copper 1 plus is the brick red in this case. The solutions only differ in what the other one uses tartaric acid in the mixture and the other one uses something else. Right. Okay, so these are all the different types. Have a look at this document, see if you can, even in your head, try and work it out. So here is something that came directly after question 1, where you had to draw the or name or draw. So remember, it was this particular one, and that you had to either draw this one and name that one. Now they say, how would you distinguish between them? And it's again the observations, the type of reaction. It's the standard questions that come up again and again. Okay. And here is now a case where you get given 3 or 4. This one's 3. You need to develop a procedure. And a common thing for students is to start, acyl chlorides react with water. So you can find out which one is the acyl chloride by adding water. And if there's a reaction, then you've got the acyl chloride. Don't ever start that way. Don't sort of like assume you know what the unknown is. You need to start something like this. Add water to all 3 liquids. Only the one that's got the butanol chloride in will show a reaction because it'll react vigorously. Okay. Then the other 2 you don't know. So now you've identified that one. Now you take fresh samples and you add sodium carbonate solution to the remaining 2 liquids. Then the one that bubbles is the one that's got butanoic acid. The other one won't. And then you say, how would I test the last one? And then you can do the potassium permanganate. So I hope that's clear. So you start off with the unknown, you add something to all 3, and then you try and eliminate. Then to the remaining ones, you add, litmus, whatever it is, bicarb, just to see what the reaction is, eliminate some more, and carry on that way. Okay, so that's theirs. Now, here's some more. So it's again the procedure, and I would suggest always start with water, because anything under 5 carbons should dissolve. The ones with more than 5 don't really dissolve. Okay, now we get to polymers. Polymers is always a big thing. Some years, 1.5 questions can be on polymers. So the types of questions you can ask for polymers is, here's a polymer, give me the monomer that makes it up, or the 2 monomers that make it up. Or it could be, here are 2 monomers. Draw 2 repeating units of the polymer they would make when they react. Or it could be you've got something with 2 different functional groups. So this is, for instance, the carboxylic acid and the amine. So we've got the same thing over here. So what will happen is this carboxylic acid can react with that amine. And if I do a different color, you can have this carboxylic acid, this carboxylic acid reacting with that amine. And that would give you two different dipeptides. Okay, and that's where they've drawn it. So if you want to have a look here, this is the blue one reacting with that one, and this is this carboxylic acid. So you can see that over here has gone over here. So this is this carboxylic acid reacting with that amine, and that's your peptide link. So here, as long as you've drawn the correct amide linkage, C double bond O NH and so on, you've got your achieved point. Okay, this is an example of find the linkage. So, you know, there's an ester link, there's an ester link, there's an ester link. Don't circle those because those are only half there. And so a very common question is, when you've got either a peptide link or an ester link, what happens when you treat it with acid and what happens when you treat it with base? Because those links break. So the best way is to say, okay, draw a line between the carbonyl and either the O or the N, okay, if you were given that. Then for the acid hydrolysis, you will form for an ester an OH. Now an OH is neutral, so it won't react further with acid or base. So that stays simply as OH. However, the COO, what happens is an OH gets added to that. Because if you think about it, you're adding hydrolysis. Hydro is water. So there's an H being added. There's an OH being added. So that's H2O. If you've got an acid hydrolysis, does acid react with acid? I hope you will say no, it won't. So that's the end of the story with an acid hydrolysis. The OH stays the same, the acid stays the same. If, however, you were asked to hydrolyze an amide link, hopefully you know that if I had, say, CH2 and this was NH2, okay, hopefully you know that amines are basic. Do bases react with acids? Hopefully you'll say yes. So under acid hydrolysis, if you had an amide, you would get your, remember that a base is a proton acceptor, so it picks up another hydrogen. We had NH2, so it's now NH3. So it's picked up an H+, so we must have a positive charge. So you do need to draw that positive charge on it. So if you're doing an acid hydrolysis of an ester, there's real no change. One is OH and the other one is COOH, COOH. But if you had an amide, then you must change the amine to a cation. With a base hydrolysis, again, an alcohol is neutral, so it won't react with a base, but the acid part, being an acid, will react with a base. So what you've got to change your ending now to a salt. So you can either make just simply the anion, or if you were given the base, sometimes they'll say they'll react it with KOH, for example, then you can put in the cation. Because remember, acid plus base gives salt plus water. So what is the salt? It's the cation of the base and the anion of the acid. So that's the anion of the acid and the cation of the base. Okay. So as I say, if you look through here, some years, there are a lot of polymer questions. So there was B, C, so there was quite a bit there. Other years, there's not much at all. So I think it was 2020, there was a heck of a lot on polymers. Yep, they had a lot on polymers. Right, so please make sure you know how to do those different things. Can you draw the monomer? So for example, here, okay, they just want you to identify the peptide link. So those are all peptide links. So that's very easy. So it's a very easy achieved point. And yep, here you might need to draw the two monomers. So for example, they join together. Oh, hang on. I'm looking at the answer, not the question. So the question is they give you two things. So here, this will react with that. And then another one will join on over here. So it's just like a repeating thing. So draw this in again over there. And then this bit gets joined on over there. And each time you make a join, you take off H2O. So there's always two hydrogens and oxygen gone. So it's normally that OH and that H, one of them that's gone. And as I say, please pop in questions if not explaining properly. Okay, now last thing is reaction schemes. I think that is the last one. Yep. Reaction schemes you are going to definitely get. Sometimes they're quite detailed like this, where these in red are all the ones you need to fill in. Okay. Others are, they just simply give you a whole lot of information, and then you've got to work out what those intermediates are. And sometimes, and often these are the hardest for students, they'll say, I've got butanone. Tell me how to make butane 2,3-dione out of it. In other words, I want to have another ketone over here. And that can be quite hard for students. So these are tend to be the hardest. And when you do this, I suggest you work both forwards and backwards. So for example, think of what can you do with a ketone? And that's where those cards that I showed right in the beginning can be useful. So what can I do with a ketone? Well, I can make an alcohol out of it. I can, or I can go from an alcohol to a ketone. So if I go back here again to over here, ketone, there's not really that much you can do with a ketone. A ketone, you can either sort of go backwards to reduce it, or you can go from a secondary alcohol to a ketone. So that's one step you could do. So you could go, okay, I can go from a secondary alcohol to a ketone. So that's sort of step over here. Okay. But that means I've got to now try and get an OH there. So just sketch out what would it look like. CH3 COH C double bond O CH3. And you think, well, how can I get an OH there based on just a carbon? And the only one you know is I've got to have an alkene of some sort. So how am I going to do an alkene? And so you to get that, the you can react. Now this is level 2 work. So if you don't remember, the level 2 work is if you treat this with Cl2 and UV light, you can go to the CH2Cl to COOCH3, although quite frankly the Cl could add there as well, so it's not the best. Oh, I left out a CH2. And then you can go from there to the alkene. Okay, and then from the alkene you can treat that with because it's going to be the major product, because I want my OH to land up on the second carbon. So you can treat this with your conc H2SO4 and water, and that'll get you from there. If however you are struggling with this because you don't remember that from level 2 chemistry, or you never did this in level 2 chemistry, that's not going to work. So the way they've done it here is they've just simply said, okay, I'm just going to actually start from that is my reactive group. In my ketone, the only reactive group I've got is this one. So I've got to work with that. And again, when we pointed out what can we do with a ketone, the only thing we can do is reduce it. There's no other reaction given. So in terms of the answer is they've wrecked the ketone. So although we want to end up with a ketone, they've actually finished, they've removed it. So they've taken the ketone away to form the alcohol. And then from the alcohol, they have done an elimination to get the alkene. Alkenes are very useful intermediates. And when they've done the alkene, they've treated it with permanganate. And notice they have said neutral conditions. And that'll be important, particularly for an alcohol. It does work with acidified, and I will notice some past papers accept the acidified to go from an alkene to a diol. It's just the acidified is a stronger condition, a stronger reagent, and you can often break that to form carbon dioxide, you form a carbon dioxide type thing. So it tends to be that you use neutral. So it goes from purple to brown permanganate in that reaction. But that now means I've got an OH, which means I can now reflux. So here we were just simply oxidizing it to the diol, but now we're going to be refluxing it over here to form the ketone. So whenever, as I say, these can often be the hardest. So work from both the back and the front, and don't think that you have to keep something the same. So don't think, oh, I've got a ketone there and it stays there, so I can't touch that because I've got to have it in the second one. You can still change it and move it back again. Particularly if you, as I say, even this method I showed here is not the best method because, quite frankly, this one could be chlorinated as easily as that could be chlorinated, and then you'll really go wrong. Okay, so that's pretty much it for the reactions. Totally unrelated questions, but are haloalkanes polar or non-polar? Right. They are polar. They do have a dipole moment. The problem is the degree of polarity. They are not particularly polar. And the way we often treat it in organic chemistry is often a branch by itself. We do a sort of a what's practical rather than let's do the absolute theory of it. So in CH3.4, you would definitely say it's polar because when you do the shape and the bond dipoles don't cancel out and all that sort of thing. However, in organic chemistry, we do sort of say yes, it's polar, but it's not soluble. And the reason being is that water, of course, can form hydrogen bonds. And those are quite strong bonds. And you've got to break those strong hydrogen bonds. So that is the hydrogen bond. This is not the hydrogen bond, hey? This is the hydrogen bond. You've got to break those strong hydrogen bonds. And that energy has to come from somewhere. So if I've got a haloalkane, so you've got a slightly positive end and a slightly negative end. This is where they Cl is or something like that. This doesn't form as strong an attraction with the oxygen, the slightly positive end, because it's not as polar as you'd want it to be. So if you've done the 3.4, you've got your permanent dipole forces of attraction, but they're not particularly strong. So the energy released in this attraction is just not enough to break the hydrogen bonds. And therefore, haloalkanes, in spite of being polar, don't dissolve in water, or not enough. And you'll find you'll always form two layers. Depending on how many halogens are attached, the halogens are at the bottom and the water is at the top, because halogens are normally more dense than water. But it depends what you've got. Sometimes if there's only one little halogen present, it goes to the top. However, your ketones, your aldehydes, your amines, not your amides, your carboxylic acids, and your alcohols. As long as they're 4 carbons or less, will all dissolve. Now, hopefully you know that these will all have hydrogen bonds because they've all got that OH, the same thing as they've got there, or they've got an NH. And NH, remember, has made that hydrogen naked, so that that hydrogen will hydrogen bond onto another nitrogen of another molecule. Ketones and aldehydes do not hydrogen bond by themselves. So that's why aldehydes have got low boiling points, and ketones as well. However, if I had a ketone here, so CCOC, right, as I say, there's no hydrogen here, so it doesn't hydrogen bond with itself, but this is still slightly negative, and that's slightly positive. But it's not the fact that it's got that dipole there, it's the fact that this hydrogen in water, remember, it's naked, okay? It's got hardly any electrons. So it's pretty positive. And it's just looking for any place that has got excess electrons. This oxygen, I mean, if I had another water molecule, that oxygen would be it. This oxygen is actually got even more negative charge because, well, no, it's got about the same. Don't forget what I said there. But can you see this oxygen is not the same as that oxygen? So it can form a hydrogen bond. And that's why ketones and aldehydes, although they can't hydrogen bond with themselves because they don't have that hydrogen, when you put them into water, which does have that available hydrogen to hydrogen bond, the water will hydrogen bond with it. And therefore aldehydes and ketones will dissolve in water, particularly if they've 4 carbons or less. If they're longer chains, 5 is sort of in between, but if they're 6, so hexanol is not soluble in water, hexanoic acid is not soluble in water, and that's, well, not particularly, you know, it's very, very minimal, and that's because that non-polar end is just too big. Okay, so that's about it. I cannot help you with learning the reaction schemes. You need to look at those cards and learn them yourself. All I can do is give the tip of don't just start on one end and try and work all the way through. Work from the top, work from the bottom. Look for any clues in the middle to help you out. And as I say, the more you know those reactions in your head, the more ideas you'll get when you're trying to look to see what to do. Okay, any other question? Right, so I'll stop recording and I will send out the link later, and I will also correct the mess up that I had there. I put it in the wrong part. Okay. Have a good rest of the week. I will, yeah.